Hello and welcome back to episode 2 of quantum mechanics. The first episode was a brief introduction to why quantum mechanics exists at all. Why do we even need quantum physics? This one we are going to look a little more into the bigger picture and go a little deeper into some of the concepts in quantum mechanics. So stay subscribed, make sure you put some comments down there, and for all the people who've been giving me some wonderful feedback, thank you. Please continue watching, and of course feel free to correct me if I'm wrong. I can see that some of our viewers are actually more knowledgeable on quantum physics, so feel free to correct me. So with that, let's get started. So quantum mechanics, the big picture. So for most of human history, reality felt really intuitive. Objects kind of stayed where they were unless you pushed them. Stones fell downward. The sun rose and set with dependable regularity. If something moved, there was a reason, a force. Something has to be pushed. So this intuition shaped not just daily life, but the earliest scientific thinking about the universe. So when physics matured in the hands of Newton, Galileo, Maxwell, it felt as though humanity had discovered the true language of nature. It felt as if these few equations could predict the motion of planets, the arc of a cannonball, flow of electricity, everything. So the universe appeared orderly, mechanical, and deeply rational. By the late 19th century, confidence was very high. Many physicists believed that all the great discoveries were already done. It's over. What remained though was just refinement, adding some decimal places, improving measurements. They could not have been more mistaken. So let's look at the first assumption they made, the hidden assumption. Classical physics rested on an assumption so natural that no one questioned it. That assumption basically states that the laws governing the universe are the same at all scales, whether it is at a planetary level or at human scale or at atom scale. The laws just hold good. If Newton's laws work for apples and moons, surely they should work for dust and atoms. Or if Maxwell's equations describing light crossing continents, they should be able to describe light interacting with matter itself. Those were the assumptions. These assumptions felt obvious, right? After all, why would nature suddenly change its rules simply because we are looking closer? But nature had a surprise. So let's do a journey into the small. Imagine zooming out from Earth, going outwards towards you can start seeing the continents, oceans, cloud systems. You zoom further out, the Earth becomes one more planet orbiting the sun. You pull back a little more, the solar system, the galaxy, all of these things. At these scales, classical physics really shines. Motion is smooth, paths are predictable, forces behave exactly as expected. Now let's reverse the journey, zoom inward. From your body to cells to molecules to atoms, here the familiar rules begin to falter, or they kind of start to break. At the atomic scale, matter is mostly empty space. Just like you imagine a solar system, between planets there's a huge void. There is so much empty space that you can't really imagine it. The same thing happens at an atomic level. You go deep down, electrons and the nuclei are separated by huge space. So electrons do not orbit the nuclei like miniature planets. And at that scale, energy does not flow very smoothly. And at that scale, light behaves inconsistently. So the deeper scientists looked, the more reality seemed to resist our normal classical understanding of physics. So the first cracks in physics started to appear, the cracks in classical physics. The first signs of trouble, they kind of appeared very quietly. Hot objects emitted light, but not in the way classical theory predicted. According to existing laws, a heated object should glow brighter and brighter at shorter wavelengths. A prediction that led to an absurd catastrophe called the ultraviolet catastrophe. If you keep on heating an object to brighter and brighter and hotter, you reach such short wavelengths that you'll actually lead to an ultraviolet catastrophe. Reality, however, refused to explode into infinite energy. Just because you heated it so much, it doesn't give you infinite energy. That doesn't work like that. Then came the photoelectric effect. Light shining on a metal surface would start ejecting electrons, but only if the light had enough frequency, regardless of its intensity. So atoms too kind of started behaving strangely. When excited, they emitted light at precise colors, like fingerprints, not the smooth rainbows we are expected to seeing. These were not small discrepancies, they were deep contradictions. So the assumptions we made on the smaller scale universe started to break. So these were the first few cracks in classical physics. And that's how quantum mechanics, quantum physics, it all started to come into place. So this is an area where common sense stops working. At human scales, common sense is reliable. Objects have definite positions, causes lead to effect, motion unfolds smoothly through time, all of these things. Particles behave like waves, waves behave like particles. There is no uncertainty, it's clear. Energy appears in very discrete jumps rather than continuous flows. So observation itself seemed to influence some of the outcomes. So this wasn't because scientists lacked imagination. It was because human intuition evolved to survive in a world of trees, stones, predators. We did not evolve to live among electrons and photons. We just assumed they're inside us. So the quantum behavior suddenly started feeling very strange. We were never meant to experience it directly. Now that we are observing things at such a close level, we start seeing these discrepancies. So the crucial realization that came out of this is that scale matters. The breakthrough came with a very humbling insight. Classical physics is not wrong, it is limited. It works when the objects are large, when energies are moderate, distances are visible. But at very small scales, reality follows a different logic. Just as Newton's laws gave way to Einstein's relativity at high speeds, they also gave way to quantum mechanics at microscopic scales. So this means that the laws of physics are not universally identical at all scales. Instead, different sets of rules or approximations apply depending on the scale being considered, such as the macroscopic world of planets or the microscopic world of atoms. Understanding that the behavior of the universe depends on the scale at which it is observed, that the laws themselves can shift from one scale to another, this kind of transformed our scientific thinking. So the reluctant birth of quantum mechanics. Quantum mechanics was not born from philosophical curiosity or something. It was born because of necessity. Some of the rules started breaking, some of the assumptions no longer hold. Max Planck introduced the idea of energy at a quanta level. So, as a mathematical trick, Albert Einstein proposed that light came in packets, photons, not because he wanted to, but because experiments forced him to do that. And Niels Bohr, he rebuilt the atom using assumptions that violated classical intuition at that time. Each step felt very wrong, and yet each step matched the reality that they were observing. Quantum mechanics emerged piece by piece, pieced it together by those who doubted their own proposals, but they trusted the results, the evidence. So gradually a new picture of reality started forming. What quantum mechanics revealed was very unsettling. At its foundation, reality is not continuous. It is something hard to imagine unless you've heard of this concept before. Reality is not continuous. It is not deterministic. It is somewhat uncertain. It is not fully independent of observation. So if you observe it, the behavior or the reaction of the observed might actually change. So instead, the new picture of reality is it is discrete at a small level, it is probabilistic at that small level, and deeply intertwined with measurement and how we are observing it. So all of this applies at the small level, at the molecule atoms level. So particles do not have precise position until they are measured. If you remember in the last episode, I mentioned it's hard to pinpoint where an electron is at any point in time. It's only a probability. So outcomes exist as probabilities, not certainties. The universe at its smallest scale is not a clockwork machine. But if you zoom out, the macro world that we are looking at, that looks like a clockwork machine. But at the smallest scale, it is a field of possibilities. So this is the most experimentally verified theory in human history so far. So why this changes everything? Quantum mechanics is not some abstract curiosity. It explains why atoms don't collapse, why chemistry exists, why materials behave differently. It goes a lot into modern electronics, and it also touches upon quantum computing. So that was just a quick primer about what quantum mechanics is about and what we are going to study in the next few episodes. So with that, I'm going to wrap up this episode quickly. Quantum mechanics exists because reality really left us no choice. The universe refused to behave as we expected. It demanded a deeper framework. So this marks the shift from classical certainty to quantum uncertainty. And that's what we'll study in much deeper length in the upcoming episodes. So please do subscribe and let's keep the journey going. Thank you for watching.